Hi everyone, this will be our lecture on Chapter 8, which will be covering properties of gases. So what I've done is divide up the theory and the practice problems into two sets of videos. So this particular video will cover the theory in Chapter 8, while the other videos that are on YouTube have covered representative practice problems from each section. So why don't we get started? Chapter 8.1, we're going to start discussing the properties of gases and the variables and the physical quantities that we need to know to describe how gases behave. So on a microscopic level, we describe the behavior of gases using kinetic molecular theory. So our definition of a gas, rather than just being a compound that fills its volume of its container, we need something a little bit more refined to describe how gases interact with each other, and eventually that will lead us to how molecules react and actually a chemical reaction occurs. Right now we're going to assume no chemical reactions, and we're just looking at how gases behave when we change physical properties. So for us, a gas is a rapidly moving particle, and they only move in straight lines until they hit something, and then they would change direction. They essentially have no attractive or repulsive forces, so they basically behave as individual units and they just bounce off each other. They usually are very far apart. So it's part of the reason why it's so easy to move your arms through the air. Even though you're pushing molecules out of the way, mostly it's empty space. Those molecules are just moving around in very wide, relative to each other, their size, large space. And so they have very small volumes compared to the volume of a container. So we know how small an individual atom is. We're on the order of magnitude of picometers. And if you're talking about a liter, you're probably on the order of magnitude of centimeters. So it's a very large difference between how voluminous a particle is versus the volume of the container when you compare the two. And then finally, and we'll talk a little bit more in detail about this later, is that as the temperature increases in a sample, the kinetic energy, or how fast those particles are moving, will increase. So actually what we perceive as temperature is actually just a perception of how fast the molecules are moving. We just perceive it as heat. So the variables that we'll need to know to describe a gas, there's 4 of them. We've discussed all of them in previous chapters, but let's put them into context of how we're going to use them for this chapter. So the 4 properties are pressure, volume, temperature, and amount. I don't think we've used the symbol N before, but it stands for number of moles. So we have our lowercase n. Pressure is usually reported in a couple of units, either atmospheres, which is more common, millimeters of mercury, or Pascal. Torr is also used as well, and that's actually equivalent to millimeters of mercury. Volume, for the most part, sticks with SI units, typically reported in liters or milliliters. And then temperature for us. For these calculations, because we cannot have negative numbers or the number 0, temperature will be has to be in Kelvin. And so you've probably already seen that if you've seen the practice problems that we've done. So that's the one thing that we need to make sure we keep in track of. Kelvin is the only scale we use for temperature when using the gas equations. And then we're going to deal with amount. Typically it's not in grams, it's almost always in moles. And actually for the calculations to work, it must be in moles. And we've discussed this before, right? 1 gram of hydrogen does not contain the same number of atoms as 1 gram of carbon. So the first is volume, and we've seen this before. Right, so gases behave by taking on the volume of the container that they occupy. It's usually measured in liters and milliliters, and like we said before, it typically increases as temperature increases, as long as the pressure is constant. And you might have seen, well actually, I don't know if you've seen it in real life or not, but hot air balloons work on this idea, that as the temperature increases, right, the volume is going to expand, and that's actually how you inflate the hot air balloons. Temperature, like we already said, temperature has to be on the Kelvin scale, or else the equations fall apart entirely. The big take-home message, because temperature is actually a macroscopic phenomenon, is no such thing as temperature per se on the microscopic scale. On the microscopic scale, we're dealing with kinetic energy, so how fast they're moving. So for us, when the temperatures decrease, the molecules are moving slower, so they're going to have fewer collisions. And when we increase the temperature, the speed of the molecules increases, so more collisions are happening. The reason why we're talking about collisions right now is it's more foreshadowing, because later we're going to find out that collisions will be necessary for chemical reactions to occur. But in Chapter 8, we're assuming no chemical reactions. So pressure, we'll spend a little bit more time on this. So pressure is the measure of a gas particles colliding with the side of the container. So pressure occurs when the molecules smash into the side of the container and change direction. Some of their energy is transferred to the side of the container as force, and that's actually what's keeping something inflated like a balloon. So you have a party balloon, you fill that up by exhaling gas into it. More particles are inside it, and they crash against the sides more often because there's more of them, and it will inflate the balloon. So there's a couple of different units that we'll be introducing for discussing pressure. So that's millimeters of mercury, which sounds like a measurement of length, which it actually is, and we'll get into that in a slide or two. But when it's reported as millimeters mercury, or in the United States, sometimes you'll see inches mercury, is a unit of pressure. And millimeters mercury is going to be equivalent to torr, which means it's just their 1-to-1 ratio. So 1 millimeter of mercury equals 1 torr. Probably the most common way to report pressure in science is going to be in the unit of atmospheres, which 1 atmosphere is equivalent to the pressure at sea level on Earth. The SI units of pressure are Pascal or kilopascals. Pascal is such a small unit that kilopascals are often used in everyday science. Another common one found in the United States is pounds per square inch. So you've probably seen this filling up your bike tires or the tires in your car. So the gas particles in the air, so we're surrounded by air, right? They're exerting a pressure on this, and we're going to call that atmospheric pressure. And almost under all circumstances, it's roughly 1 atmosphere, though it does change if you go to higher elevations, say if you were in Denver, Colorado, or if you're on the top of Mount Everest. The pressure actually goes down as you increase in elevation. But for us, usually atmospheric pressure, especially at Boston at sea level, will be 1 atmosphere. So measuring pressure, that's done using a barometer, and I think most people have heard of that term before in grade school. So it's just an apparatus that measures the air pressure surrounding the instrument. So this is a good example to show why millimeters of mercury are a measurement of pressure despite looking like a measurement for length. So what you see on the right-hand side is a petri dish filled with mercury, which is a liquid metal at room temperature. And inside the test tube was originally a vacuum, but the atmosphere around the test tube is pushing down on that sample of mercury, and it actually pushes it up the tube. What you measure with a ruler, how far that mercury rises up the tube, is measured as a distance, but it's equivalent to the pressure that's being exerted on it. So this is a table summarizing all of our units for pressure. I will give you the conversions on any exams, but it's up to you to be able to recognize if I say a unit name or a unit abbreviation, that you would recognize it as a unit of pressure. For us, I will stick to atmospheres, millimeters mercury, torr, inches mercury. Actually, I'll do them all. So I'll just let you guys know the conversion factors on the exam. The only reason I would include some of the imperial units, like pounds per square inch and inches mercury, is because as nurses, a lot of time the blood pressure, I don't know, I'm not a nurse myself, but when you're taking blood pressure measurements, it's reported in inches mercury. So this moves us on to section 8.2. So the next subsequent sections will all be discussions of individual gas laws. And what we mean by laws are equations that describe how gases behave under certain conditions. So the first that we're going to discuss is Boyle's law. So Boyle's law states that if volume decreases, the pressure also increases. However, we need to make sure we set constraints because we have 4 variables. We have P, V, T, and N. So for Boyle's law to be true, we have to hold 2 of them constant, and that will be temperature and the number of moles. So what we see why this law holds is the example we see on the right-hand side. So if we have a container here, it's filled with gas, and it gives us a certain initial conditions where we have a pressure of 1 atmosphere inside and a volume of 4 liters. What ends up happening is the piston here is going to push down on the top, effectively making this a smaller volume, and that's what we see here. This is the new conditions, where it has a smaller volume, well, it has the same number of particles moving at the same speed, because there's my number of particles, and effectively telling me the speed of the molecules. So they're moving around really fast in smaller spaces, so it means they're going to collide with the sides of the container more often. If they do that more often, the pressure goes up, and it's exactly what we see. The second law that we'll discuss is Charles' law, which is going to relate temperature and volume of a gas. So just like with Boyle's law, we need to indicate what our conditions are. So again, since we have 4 variables, 2 of them are going to need to be held constant for Charles' law to hold. So in this case, pressure and the number of moles has to remain constant. So Charles' law, expressed here, right, is going to give us how the volume and temperature are of one condition. Then I change something, and it's going to tell me what those conditions are for this second system. A good example here is, here's our initial, or V1T1. So this is our first condition. We have this container. It has a piston, but this time, instead of pushing down on the piston, we're just going to let this piston slide on its own. So here we have some gas, it's inside a certain volume, and it has a certain temperature. So in the way this represents it, there's a flame underneath it. As we increase that temperature, the volume is going to increase. Why? Because those molecules are going to start moving faster, which means they start to collide with the sides of the walls more often. If this is allowed to freely move, what that's going to do is then push up. And what it's going to do is push until the inside pressure equals the outside pressure, and it's going to establish this new volume. And we can see here the temperature went up, the volume also goes up. And this also explains why when you heat a hot air balloon, the balloon actually will inflate just by heating the gas itself, which the gas would be air. Our third law is going to be Guy-Lussac's law, and this is going to relate temperature and pressure of a gas. So again, we have our conditions, where in this case it will have to be constant volume and the number of moles, so the amount of stuff or gas that I have in the system. Here we can see we have the pressure and temperature of the system initially, and then we perform some change on it, and then we can calculate what that change will occur in terms of pressure and temperature. So what we see here is we have another sample. Here we have our container, it's filled with gas molecules, we have a certain temperature and a certain pressure. Here, again, we're not allowing this piston to move, unlike in the last example. So this volume is fixed because we have our constant V. The temperature goes up, that increases the speed of the molecules or their kinetic energy. They hit the sides of the container more often, and that is going to be our readout of pressure. So increasing the temperature is going to increase the pressure of the system. We've now introduced 3 gas laws, and actually we're going to find out we can mathematically combine them. So what it's going to allow us to do, instead of changing one variable at a time, we can start to change 2 variables and ask, how is the system going to respond? So the combined gas law combines Boyle's law, Charles' law, and Guy-Lussac's law. We're not going to do the math out or derive the equation, but what you can do is set up an equation where all 3 of them can be substituted in, and what we end up with is our combined gas law, where we know the pressure, volume, and temperature of a system under one condition, and then we can make 2 particular, it doesn't matter which 2, but we can change 2 of the conditions at once and then ask what happens to the third. And so this is going to be a very useful equation, because technically you only need to know this equation to back calculate these other 3, but we'll discuss that in a little bit. And that little bit will actually be right now. Right, so what we see here is the combined gas law. It's actually represented 3 times. But here, right, we've discussed our conditions for Boyle's, Charles, and Guy-Lussac's law. And it had certain constraints. One was temperature and the number of moles for Boyle's law, pressure and the number of moles for Charles' law, and volume and the number of moles for Guy-Lussac's law. So what we actually see, so N never appears anywhere in the combined gas law, so that's fine. We don't have to worry about N. But T, P, and V do. But if we look here, T is constant. Well, that means temperature 1 must equal temperature 2. If they're equal, they can cancel out, and look, from the combined gas law, we have now just pulled out or derived Boyle's law. And we can do the same thing for the other 2 gas laws. If pressure is constant, well, P1 must equal P2. If V is constant, V1 must equal V2. And what we do is we see again the combined gas law will then be simplified down to either Charles' law if it's constant pressure, or Guy-Lussac's law if it's constant volume. So we can see it's not like we have three individual laws. It's actually one law governing how gas behaves, but we can pull out particular behavior as long as we keep certain variables constant. So what we're going to do now is start introducing, well, what happens when we start changing the number of moles? In particular, we're going to be looking at volume and how volume is affected by adding more gas or subtracting gas, which is effectively adding more moles of gas or taking away moles of gas. And so we're also going to introduce the concept of STP, which stands for standard temperature and pressure. And another take-home message, which we'll get to in a couple slides, is going to be that for all gases that behave ideally, which means sometimes they don't, but if they do behave quote-unquote ideally, 1 mole of gas would fill exactly 22.4 liters of space or volume. So let's get into one last law. We have, well, second to last law. We have another law that describes gas behavior, but not necessarily changing variables. That's going to be Dalton's law. We'll see that at the end. But Avogadro's law is going to be the law where we ask the question, well, what happens to the volume of a system if I change the number of moles? So like the other gas laws we saw, we have to indicate our conditions. So for Avogadro's law to hold true, the temperature and the pressure must remain constant. You also can, it might be maybe helpful to remember Avogadro's law. It's the same guy who's named for the concept of Avogadro's number is named after. And then what you'll realize is Avogadro was responsible for introducing the concept of moles. So we know Avogadro's law is going to be dealing with how number of moles affect the system of a gas. So what we see is we have our conditions for the first system. I can make a change and then solve for how the system responds to that change. So what we see here is we have a container. This time again, this piston is going to be allowed to slide. So certain conditions are allowed to, the piston's allowed to slide. That's only when we don't have constant volume. So I have a certain number of moles of gas and they have a certain volume. If I put in more particles, the volume increases. And this one should probably be one of the most intuitive laws, because this is like blowing up a party balloon. If you exhale into a balloon, you're putting CO2 into the balloon, more than originally was there, and the balloon inflates. It's exactly equivalent to Avogadro's law. So, standard temperature and pressure. We're going to introduce, so we've talked about all the laws. We've talked about particular conditions, and now we're going to state a standard condition, something where when you're reporting properties of gases, things can change between different laboratories when experiments are done. So to keep everything comparable, scientists have developed certain particular standards that we'll use. And then one of them is standard temperature and pressure. So standard temperature is going to be 0 degrees Celsius or 273 Kelvin. And then standard pressure is 1 atmosphere, or 760 millimeters of mercury. And so if you're reading a question or someone says STP, you immediately know under what conditions of temperature and pressure are being considered, which is useful for Avogadro's law because temperature and pressure are constant. So under STP, right, we know T and P would be constant, and then we would just use Avogadro's law. So it's a helpful abbreviation and a helpful standard that other scientists can compare their results to basically standardize what they're reporting. So how does molar volume respond to STP? So what do I mean by molar volume? So actually, if we go back here to Avogadro's law, we see we have moles and volume. Molar volume just is effectively saying it's the amount of volume per number of moles in that system. This is the definition of molar volume, V over N. For all gases that behave ideally, and for us, we don't define ideality. So I'm just saying that to be technically correct, but for us, we're going to stick with all gases will behave like this, as long as they're simple. For all ideal gases, 1 mole of gas is going to occupy 22.4 liters of volume. So this is going to be the molar volume of a gas. And as long as STP doesn't change, so don't change the temperature, don't change the pressure, it will always, all gases will have 22.4 liters as their volume. What this allows us to do, combining STP and Avogadro's law, is to create a new conversion factor, where we can either write 1 mole of gas will have a volume of 22.4 liters, or if I have 22.4 liters and fill it with gas, the number of moles of gas will be 1 mole. And this is what we see here in this figure. If I have 1 mole of helium, or 1 mole of oxygen, or 1 mole of nitrogen, they all contain the same number of particles, though they all are chemically different. Yeah, I have a different mass for each, and this is why we said in the start of the video, you're not going to see mass show up in any of the gas laws, because it varies, right? However, if we keep our STP, I keep losing the mouse, sorry. There's my STP in bold. Well, what we see, the volume of each balloon is 22.4 liters. It's a huge balloon, but this is showing us that molar volume of a gas doesn't care what its identity is, it just cares how much gas I have. And now we're going to move into our final section of Chapter 8. So everything we've dealt with so far has either just been a generic gas where we don't say what type of gas it is, or it's been a mixture, but we really haven't talked about the individual gases in the mixture. So imagine you had a mixture of like air, where it's nitrogen, oxygen, carbon dioxide, argon, and other trace gases. So it's a mixture, right? Dalton's law is going to deal with how does the total pressure of a system behave if you change the number of moles of individual components of a mixture. So partial pressure of a gas is the pressure that each gas in a mixture would exert if it were by itself. So what we see here as an example is, if imagine we have a tank, all these tanks have the same volume. So we have helium in tank 1 under 2 atmospheres of pressure. So those molecules, that's the pressure if helium was just by itself. If I emptied that container, then filled it with argon, and this time under 4 atmospheres of pressure, so there's more argon put in because the constant volume, constant temperature, right? So the pressure has now gone up. So the pressure exerted by helium by itself was 2, pressure exerted by argon by itself was 4 atmospheres. If I combine that as a mixture and have both argon and helium bouncing around in the same volume, what we see is, according to Dalton's law, the total pressure is just the pressure exerted by the helium plus the pressure exerted by the argon gas. So 2 plus 4 is 6, and it's exactly what we see as the readout on the container. So Dalton's law of partial pressures indicate that pressure depends on the total number of gas particles. It does not care what the chemical identity is. So that's what we saw, helium and argon mixed. Didn't care that they were different. It just cared how many particles were in there. And that the total pressure exerted by the gas in a mixture is the sum of the partial pressures of those gases. So in this case, if I have 3 different gases mixed together, 1, 2, and 3, I already know it doesn't matter what the identities are, so maybe it's oxygen, nitrogen, and argon, who knows. If you know the individual partial pressures, you can add them up and get the pressure total. And this will work for an infinite amount of gases, and that's why the ellipses at the end. You can add as many as you want together, and it will, if it follows Dalton's law, you can add them up to find out the total pressure. So this is basically what it's showing here. 1 mole of, I keep losing the mouse, there we go. 1 mole of nitrogen gas is going to have the same total pressure as if I had 0.4 moles of O2 and 6 moles of helium, as long as I have 1 mole of gas. Or maybe I have a half a mole of O2, 0.3 moles of helium, and 0.2 moles of argon. It still totals to 1 mole. All of these will have the same pressure of 1 atmosphere. It does not matter what the chemical identities are. It only matters on the amount. And so a common gas mixture is going to be that of air. So I just wanted to mention that in this lecture. We're not going to do too much with it, and I think most people are familiar with this. But sometimes it does surprise people to think that, yeah, there's a mixture. Oxygen only makes up 20% of the air we breathe. Most of it is nitrogen, around 80%, and everything else is trace. Air is a fluid. It moves, right? So you can move your hands through it. It doesn't feel like much, but it's still there, right? And so the pressure, because we're essentially in a sealed system, when we're looking at all those pictures, it looked like, we have a small volume. Well, Earth is a contained volume. Earth has gas in it, so therefore that atmosphere is going to exert a pressure, and that pressure is what we call atmospheric pressure. We can also divide it down into individual parts and say how much is nitrogen contributing to the pressure, how much is oxygen contributing to the pressure, how much is water or carbon dioxide or any other trace gas contributing to the pressure. And so that's going to end our lecture on Chapter 8. So I'd recommend, if you haven't already done so, checking out the practice problems that are already up on YouTube. So that has the step-by-step walking you through select problems. And then I've also included the Chapter 8 handout, which has additional problems that you guys can try on your own. All right, I would usually say I would see you in lecture or in class, but that doesn't seem to be the case. So last Friday before spring break was probably the last time I will see you guys in lecture. So I will see you, hopefully, well, not hopefully, I will see you online in a couple of days. See if I can pause this thing. I keep losing the, I kept